Hi, I'm Tommy, and I'm a developer from IBM. And my coworker Animesh, unfortunately, he couldn't make it today because he had a conflict with his schedule. But I will leave his Twitter link underneath so you can get in touch with him. And today we are going to talk about how to deploy and use a multi-framework distributed learning platform on Kubernetes. So I will go over the agenda for today. I will go over the overview for my team, Code, which is an open source team. Then we'll go over how AI and cloud is complementary to each other, and we'll introduce our open source project, Fabric for Deep Learning, and how to leverage the platform to do distributed learning. So our team, Code, stands for Center for Open Source Data and AI Technologies, and our goal is to aim improving the enterprise AI lifecycle in just using open source projects. And some of my projects done in the team is Fabric for Deep Learning. It's a platform to provide a scalable, resilience, and fault-tolerant deep learning frameworks to train on Kubernetes. Another project we're working on is the AI Fairness 360, which is a Python package, open source, that helps detect and remove biases in machine learning models. Another project we've done is another Python package called Adversarial Robustness Toolbox, which helps to create adversarial machine learning using your existing classifier. Then we also have something called Model Asset Exchange, which package all the machine learning and deep learning model we develop and let application user to able to apply it instantly on their applications. We also have like enterprise gateway, which able to turn your local Jupyter Notebook kernel and send those workloads to a remote Spark cluster and Kubernetes cluster to execute it. And lastly, also a active team that contributes to Spark. So you go to any Spark conference, you will see my coworker working around there. As our goal of team is we want to create an end-to-end AI solution just using open source technology. And as you can see, we have already contributed some of the main open source project on the pipeline doing analyzing data, machine learning, deep learning, and deployment on models. So now I'm going to introduce how AI and cloud is complementary to each other. So why AI needs clouds? AI, especially on deep learning workload, requires extensive computing power, so we need a way to do high performance computing and elaborating GPUs to accelerate the workloads. Also on cloud, you have the ability to scale your AI workloads with your AI apps as long as your AI apps grows. Also, when you try to elaborate the high-performance computing, you encounter many problems such as how do you parallelize all the models and data, and you have problem encountering when you try to scale up with internal communication using MPI, or you want to scale up with multiple GPUs in single node with NICs. And to do that, we need to make it cloud native for the AI workload, which means we need like microservices to manage our lifecycle on our AI workloads, and we need to create containers to make it a stable environment. And then we need to create automations on the DevOps teams to be able to automate this process so we don't have to do the step all over again. And to do this, we introduced our project Fabric for Deep Learning to help us make this process simpler. Fabric for Deep Learning provides a very scalable, resilient, and fault-tolerant using mechanism from Kubernetes and apply those with our deep learning frameworks. And to enable this, it's built on a microservice architecture, so it will roll out easily, easier to scale, and easier to elaborate any features that's coming new into Kubernetes. The concept here is you have a platform in your big cluster, and you have many users within that cluster that could access and allocate data, allocate resources whenever they need it. So you have a very elastic computing environments. And also, each of the each of the worker node in your machine learning workload is wrapped into a container, so you have a very stable environment, so it's easier for you to scale, and you don't have to worry about any like internal hardware infrastructure. And we've done a research paper about this deep learning platforms. And we have discussed a lot of challenges we have faced during developing this platform. For example, how we distribute different parameters and gradients using like maybe models of distributed method and data distributed method. And you could look into the research paper for more details and how we could retain the accuracy and performance with multiple GPUs. Also, Fabric for Deep Learning is also the core for Watson Studio, which is the service we provide to do data science stack on the IBM Cloud. And Watson Studio, as you can see, we provide many services, not just on machine learning, but also on data processing and data model deployments. And Fiddle is lived under the data learning runtime stack. I mean, a deep learning runtime stack. And deep learning as a service is the core, using Fiddle as a core to execute any deep learning models on Watson Studio. And Watson Studio extends that to provide a nice visualization UIs, so you could get your model status and your model metrics at a very nice UI display. And also, Watson Studio provide a very nice neural network modeler. So for deep learning beginners, they could go ahead and just use a drag and drop interface and try out how to build a deep learning models. And we have tested this platform intensively with real AI workload on IBM Cloud Kubernetes service. And one of our deployment have reached like 3,000 pods on 500 nodes on our cloud platforms. So now I'm going to introduce the architecture of the Fiddles. As you can see, Fiddle has a very complex microservice design, but when we factor it out, as you can see, we have some microservice that's more focused on the usability, such as the web UI and REST API. And there's like other microservices that handle all the life cycle of the machine learning workloads, such as the lifecycle manager and the trainer service. And we also have microservices that handle all the data collecting and metrics collecting from the models. And when you execute the job will allocate the resource from Kubernetes cluster as a pod. And then it will mount on an object storage as a shared storage to access your data set and store any models you have trained over there. And when you provision it, since it's from Kubernetes, so it will just boot the container based on the framework you have chosen, or you could bring your own container, in this case, to do your distributed learning. And we will update some release with our community partner. We partner with Seldom Core, which is a machine learning deployment platforms on Kubernetes. So we cooperate them and elaborate the model we store in object storage and use them to serve it directly on the same cluster or on a different cluster for the production workload. And then we also collaborate with H2O AI, which is a machine learning framework. We also enable multi-node cluster computing with H2O AI, so you can elaborate the same features using the Fabric for Deep Learning. We also collaborate with Harvard from Uber, which it provides a very nice MPI ring of reduced algorithms. In addition to, they also have a good elaboration between MPI and NICO communicative ends, so you could do a very nice combination of scaling out with multiple nodes and scaling out with multiple GPUs per node. And finally, we integrate with our adversarial robustness toolbox to help us detect any robustness in your models. Like your models test set might not able to cover all the edge cases in your model, so you want to calculate the true accuracy from your model in the real world use case. So now I'm going to explain my demos. The demo structure will first we will have some data going to the training and do the training process. And once the training trained a classifier models and data sets, it will it will then trigger the adversarial robustness toolbox to create a generator, use the classifier as a discriminator. From then, it will use the generator to add any noise on the original test set to verify is the classifier robust enough for this use case or not. And at the end, we also got deploy those models using seldom when the model gets stored in the same object storage. And as future plan, we also try to elaborate with our fairness checks so we could add more metrics on our models to make sure our models is ready for the production usage. And I'm going to explain a little bit on what fiddle we need for the training jobs. So it will need some model definition of how your graph is generated. Then it would need a manifest file to define how you want to execute a job, what kind of resource you might need, and where your data is stored. And then lastly, you will need to put your data in an object storage so we could easy to manage and do version control using the object storage bucket. And a little bit background on the manifest file we define is we define what kind of resource is needed within that training jobs. For example, you might need a number of GPUs and CPUs per your container and how many containers you might need for your training jobs. And then where your data is located and the credentials for how to accessing your data. And then what kind of framework you might want to use and the entry point command, how you want to execute your machine learning, deep learning models. And lastly, you can also have an option to store your evaluation metrics definitions as a TensorBoard, and we can extract those metrics on our graphic UI. So now let's begin with our demos. So first, we want to connect one of the Fiddle platform instance on our cloud. So you can see the list of training jobs I've done before. And to submit a new job is very simple. You just choose a zip file that contains all the model definition files, such as how you want to execute the models. And a manifest file that defines what kind of resource you want to use for your training model set. And then when you execute on the cloud, it will create n number of containers for your jobs. And then it will show you the status underneath as from the REST API. Oh, sorry. Is it better? I think, is it? All right. So once in this stage, you can also see what's the status of your training jobs and what framework do you use and what's the command you use to execute these training jobs. Since, for this training job, we're using the community image, so we need to install the Keras libraries and execute the deep learning models. Then we also see, once the training job running, we could also see the logs and evaluation metrics over here. So let's go to a job that's complete. So from here, you could see the log of the models. As well as the evaluation metrics over here. And an extra feature we added to this pipeline is we add a pipeline where once you train your models, you're able to do robustness check, which it will provide you an environment to check is your models cover enough edge cases. And we also enable you could deploy on the same Kubernetes cluster. So once you click the robustness check, just need to define how many GPUs and CPU you need. I think need to lower it down a little bit. And then where do you store your original models? So we could take that model and add some robustness check to it. So once you submit it, it will take some time because it will execute as a serverless actions. And at the end, we would create a new training job ID, which I think we will refresh in a second. So at the meantime, you could also deploy the models using this similar credential. It will return you the deployment URL. Yeah, I need to refresh it. So the robustness check job, it has similar to the original deep learning job. It will show you what the robustness job is doing. Basically, we'll take the original models and apply the adversarial robustness toolbox method. In this case, we're using the fast gradients attack. And once the robustness check job is done, I can show you one of the results we have over here. It will show you a list of metrics. It will show you first your original model accuracy on the baseline test data, and then the accuracy on the adversarial sample, which you can see is decreased more than 60%, which means the test set didn't cover enough edge cases for your models. And you also could see the percentage of reduction in confidence, which in this case, on average, it reduced 43% confidence rate, and the average perturbation rate is also very low, which it makes sense because we training on a fast and MNIST data set, which everything have the same background. That's why the test set didn't cover enough edge cases in this case. From here, I want to introduce a little bit on the AI Fairness 360, where we want to elaborate that in our FfDL project in the future. The AI Fairness 360 is a Python toolkit which allows you to apply some fairness check. And here is the list of available metrics you could do. So each metric has its own fairness definitions, because we cannot define fairness just using one definition. So there's several of them, depends on the use case of the models. And we also provide 10 different algorithms. How do you refine and rebalance your machine learning models using maybe reweighting on your data set itself, or enhancing your optimizer to include like fairness constraints, or you could enhance your data test set to test more edge cases to cover more fairness metrics. And you can learn more about the AI Fairness 360 toolbox by going to aif360.mybluemix.net. And I will show you a quick demo how this Python package works. So you can pick a data set from here. In this case, we do use the German credit scoring for our examples. Then it will run the fairness check with 5 different fairness metrics we defined. As we can see, the sex attribute doesn't have any bias in this case. However, for the age attribute, we can see these 4 different metrics that has bias over here. And you can see more details by clicking on the definition of each matrix. And from there, you could pick different bias migration algorithm. There's 3 types of process when you do bias migration. One is doing the pre-processing with your data. The second phase is doing the classify, where it will add constraint to your optimizer. And the third one is you add extra tests on your test case to cover more edge case uses. Sure. So for this example, we'll show you how to use the reweighting, which it will reweight the data set to be more balanced. So as you can see, after the reweighting with the original attribute, for the sex attribute, it doesn't change much. However, with the age attribute, it will reduce the bias up by a lot for each of the metrics we measure. However, it's still not enough because by just reweighting, we cannot get rid of all the biases that happen during this model, because we also need to add constraint during the training time, and we need to add more fairness check during the post-processing, which are on your test sets. And that is the end of the demos. And if you have, do anyone have any questions? Yeah, go ahead.
Go back to your resource file.
Resource file?
Yeah, where did you find
Oh, this one?
the JSON file? That's the
Oh, JSON file.
Yeah.
Over here?
You create that for each of your container, or just use one resource file for every container?
It's one resource file for every training job, so for all the container you trained for that job. Yeah, the only one. Yeah. Yes.
Thanks for the great talk. Out of all the stuff you showed today, like what can be used for free and what costs money to use?
So everything I showed today is free. It's all open source. I would say if you would only need a machine to run them, but if you don't have the machine, you could go to the Watson Studio, which it provide everything I think it will provide a lot of the feature at a free tier, and you want to expand that with a real workload, then you may have to pay. Yeah.
But is it, so Watson Studio itself is?
It's free. They have a free tier. Okay. You could try out with, I think you could try out with 2 to 4 GPUs in a free tier, and you get 50 training hour per month for free.
Okay, but then if you actually want to use more computing resources, you have to use IBM, or you can use?
You could use any cloud, because our platform is open source.
Okay.
Yeah.
Okay, thank you.
Anyone else have a question? Yes.
Is it possible to have constraints or purposeful breaks? So for example, I have one of my trainings, if I don't assert R squared, I don't want to proceed forward. Is there a way, as I build those containers to dependencies, to explicitly control the workflow between the different containers?
So we do have a way to pause, not pause, but more on halting whatever job you're running. So I think I could show you on my UI. There's a delete button. So even in the running job, during the processing stage, you could click this delete button, and the lifecycle manager would try to halt your current training job and allocate those resources for other users. Right.
But I still have to manually do. I can't be like, if I train a model, I only want to proceed forward if the model's good enough.
Good enough.
Can I stop if the model trains and it's not good enough based on its chi-square, its R-square, whatever metric I'm choosing? It's unacceptable. I don't want to spend the resources to then predict on the, the training set has been trained. The training set has been trained.
Right.
Set the model arbitrarily. Don't conduct the out of time, prediction test.
Yes, it is possible, but right now on the open source side, we only allow users to do it within their own code base. But we are planning to integrate that in the product to do it automatically for you. Yeah. Anyone else have a question? Yes.
Can you explain more into how each one job gets split up into different containers? How that process works?
All right. So let's go back to the definitions. So when you define the resource, you have to define how many GPUs and CPU resources you want to allocate for each container. And underneath, you have the learner session, which defines how many containers you want to run for that training jobs. And that determines how many resources you will allocate from your cluster. Is that answer the questions?
Yeah, but how is it, balancing that resources? So if for example, if you require 20 CPUs, how do you split up that resources so that you get the most performance out of the number of your content?
So the main resource, I think the main resource management is done from Kubernetes. So Kubernetes have a way you want to spread half of your CPU core. It could do it from the Kubernetes level. So yeah, so Kubernetes will handle everything from that level down. Yeah. Yes.
Can you talk more about when I might want to use like distributed training to solve a problem versus when I just want to train on like a single machine or something like that?
So for distributed learning, I think the best use case is when you have like a very long-running models, and sometimes your model might have a very big data set, won't able to fit into a single GPU memories. Then you might want to do like data parallelism, which is string the batch size into a small mini batch and able to fit into each small GPU you might want to run. Anyone have questions? Yes.
So with frameworks like CUDA, you can kind of like control how like a deep learning job is like distributed. So are you saying that the user in this case doesn't really need to worry about like how to distribute, because like Kubernetes like will figure that out for you automatically?
Sorry, can you repeat the question?
So there's some like frameworks that allow you to kind of like control the CUDA, like how the training is how the computation is distributed. But here it seems like you just like specify the number of containers that you want, and then you don't have to like kind of specify details of how the computation is distributed. So is that understanding correct? That
so from our example, we distribute the workload. So we in our model definition, we actually define like how do you want to communicate between the other workload node, right? So we have like multiple GPU in that workload node. We might want to use the NICO backend communication. So because you want to do the internal communication from there, and you want to have like multiple containers that have like single GPUs, you might want to use the MPI, which have a very good internal communication backend. So it varies between use case, but right now at this stage we are done within that model definitions that you define. Yes.
Can you talk a little bit more about the structure or like which files are contained in that archive? Is it file that you submit to the training service? So you said like you have like your model definition in there, so it's just like a Python script?
Yeah, it's just a Python script for my samples. But you could have a module of definition for your training deep learning model, because sometimes deep learning model could be very big, so you might want to create a whole module for that. Yeah. Anyone else have questions?
Okay, good. Well, thank you very much.
Thank you very much.